Okay, so in this video, I'm just gonna practice some system design questions. Not actually some, but just one system design question. And in this video, I'm gonna practice Facebook Messenger system. So like, I'm gonna share my screen and like pull up the whiteboard. Um, oh, I already have one shared. My bad. So yeah, we're going to design the Facebook Messenger. And speaking of the functional requirements, the users should be able to send each other texts, right? Um, and then hold on, stupid text. Okay. And then they should be able to track each other online, offline status. And then number third will be data should be persistent. So like no data should be lost. The messages should be saved seamlessly. Okay. And then what are the non-functional requirements? Non-functional requirements. Number one will be there should be low latency. So the app should be really fast. The write and read operations shouldn't take a lot of time. The app should be highly available. So in other words, make it fault tolerant. And we are gonna use load balancing and like scaling for that. Then the app should be extremely reliable and consistency should be maintained. So in other words, if I'm seeing 5 messages on my screen, the recipient should also be seeing those 5 messages on their screen. So that there should be some consistency. Data should be consistent, right? And then when I say the app should be extremely reliable, that just means that the data should be stored. If I'm sending a message, that message should be written to the database. So that's why we're going to have to talk about when we talk about cache later on. We're going to talk about what kind of write policy we're going to use. Okay. So with the requirements squared away, I'm going to clear the screen. Where's the eraser? Okay. Clear mine, clear all trunks, clear mine trunks. Okay. Um, okay. Um, so let's do some data estimation here. So let's say we have 500 million active users every day. So 500 million active users every day. And let's say they each share 40 messages a day. Each user shares 40 messages a day. Assuming that each message is, let's say, 1 kilobyte, okay, 1,000 characters, 1 kilobyte on an average. So let's assume that each message is 1,000 characters on average. It's a lot, but or rather, let's tamp it down to well, I guess 1,000 is fair enough. On average, so that's gonna be 1,000 bytes or 1 KB, right? So on an average, every day we're talking about how much data is being stored on every day. That's gonna be data that needs to be written every day is 1,000 times 40 times 500 million bytes. That's like a lot, like literally a lot. So this is gonna be 500 million times 40 kilobytes. This is gonna be 5 million times 40 megabytes. When you actually talk about gigabytes and stuff, it doesn't really seem that large, right? Like we got from 500 million to 5 million here, but it's quite large. But like just from like the absolute numbers standpoint, the calculation is gonna be a little bit easier. So then this is gonna be 500,000, 50,000, 5,000, 5,000. Yeah, 5,000 times 40 gigabytes. And this is gonna be 5 times 40 terabyte. This is equal to 200 terabytes a day. So we clearly need a lot of space. So for 5 years, um, done thinking. Um, so we assume that each message is 1,000 bytes, right? So, um, well, yeah. So 1,000 times. Okay, let me just confirm my. Let me just check my calculations one more time. 1,040, 500 here. 540 is like 5 million times 40 megabytes. So hold on. Yeah, actually I messed up here. Yeah, this is not gonna be 5 million. This is gonna be 500,000, so 0.5 million. Yeah, I fucked up here. Um, and then it's gonna be pretty much 500 times 40 is equal to 5 times 4 is equal to 20 terabyte a day, right? So we are having um so we are having 20 terabyte of data written every day for 5 years. We need um 20 times 365 times 5, which is like a lot. That's gonna be um I guess 20 times 5 is 100, right? So 365,000 terabyte. It's probably gonna be around um it's around 36 what is the unit? Petabytes, yeah. 36 petabytes here. Um so that's like a lot. Okay, and then speaking of bandwidth, this was storage. Speaking of the hold on, I'm gonna need more space than this. So this is the bandwidth now, right? So we got how much? We got 20 TB of 20 TB of incoming data every day. 1 day is equal to how many seconds? So we got 24 hours times each hour has 60 minutes, and each minute has 60 seconds. It's like 86,400. 86,400 seconds. So the bandwidth is gonna be 20 terabytes over 86,400, right? So that's gonna be, let's just see. So so right off the bat, I know it's gonna go to gigabytes because I can just eliminate the 1,000 factor here. So it's gonna be, if I were to, it's gonna be 20 gigabytes divided by 86.4 seconds. So this is gonna be oh boy, so this is gonna be 20 times 1,000 megabytes. Or it's actually 1024, but for the sake of easier calculation, I'm just gonna say 1,000 divided by it could also be written as 2 times 10,000 divided by 86.4, right? So that's like 231. So it's gonna be 231 approximately. 231 megabytes. Okay. And by the way, the source I used to prepare for the system design question is going to be educative.io. Just going to mention it due to copyright issues because I'm going to post this on YouTube later on. So educative.io. Okay, so these were the rough data estimations here. I'm just going to clear the whiteboard one more time. Clear my drawings. Okay, let's talk about the big picture, how the architecture is gonna look, right? So we're gonna have trying to see if we can like draw shapes. I'm pretty sure there was an option, draw right here. Draw a shape, right? So we have this chat server. And let's just call it chat server, right? Now this is gonna be behind a load balancer. It's gonna be one of at least 3 chat servers. So we're gonna scale this application to make it highly available. But for now, let's just say there's one chat server, right? So just gonna say that. And then we're also gonna have the clients here, right? Oh boy. These are the clients, right? So we align this. Line 1. line 2. So, and then we're gonna have a database, which is also gonna be sharded. So we're gonna like scale the database as well using sharding, but I'm not gonna get ahead of myself here. So I'm looking for a cylinder. There's a cylinder, but okay, there's no cylinder. So it's gonna use a circle. It's a database, right? We're gonna talk more about the database later on. So what is happening here, right? So let me use the arrows. So we have client one trying to send a message to the chat server. Chat server performs the underlying algorithm, right? So, and then it writes to the database, does everything it needs to do, and then it returns the message to the client, right? And so will be the case for client two. So this constant back and forth communication is happening between the chat server and the clients, which is exactly why the chat server needs to be like super reliant and highly available and fault tolerant. Because if this goes down, the entire application goes down. That's why we're gonna have more of these, but more on that later. Than the database, right? So now let's talk about what kind of database we should be using, and what is the schema gonna look like, right? So I'm gonna clear this again. Um, okay, so we're gonna start off with um, what kind of database we should be using, right? So as we saw in the database estimation, no, not database, but like data estimation, I'm sorry, misspoke. As we saw in the data estimation, we're gonna have like a lot, like overwhelming amount of data being stored every single day. A lot of read and write operations are gonna be happening. So we cannot rely on an RDBMS like MySQL or NoSQL like MongoDB, because we're gonna have to fetch a range of rows, and we're also gonna be writing short amount of data like every second, um, so it's like it's gonna overwhelm the database as well as like cause like a it's essentially gonna like break down the server, the cache server. It's gonna increase the latency. It's not feasible solution. It's gonna overwhelm the database server as well as the chat application server. It's gonna increase the latency. So that's like off the table. So what we're gonna use here is gonna be HBase, I guess. Yeah, we're gonna use HBase. That's modeled after Google's, what is that called? Oh my God, what was that? Um, gonna have to look again. Small after Hadoop, yeah, Google's Bigtable and Hadoop. So the reason we're gonna use that is because it's like column-oriented key value storage data system. So it's more like you keep adding the data to like um, a memory buffer, and then that data is dumped at regular intervals to the file storage. So like it's a lot more feasible. So we're gonna use that. um, so, okay, so how is the schema gonna look like, right? So let me use the shapes again here. I've actually worked on this chat application project before. Um, okay, so we're gonna have this. So let's start off with the user one, right? There's not gonna be like an overwhelming amount of write operations happening every second here. Uh, how do I change the color of the text? That's here. Um, user, right? So we're gonna have ID that is gonna be like the primary key, auto increment, not null. and integer, of course. How do I even change the font size? Yeah, right here. Okay, cool. Um, then we're gonna have then we are gonna have first name. Let's just say it's gonna be like what text varchar would be like 100 or whatever. Not null, and that's pretty much it. Yeah. Okay. So then we're gonna have similarly we're gonna have last name. Also gonna be text varchar 100 and not null, and then we're gonna have email, which is gonna be um no, my bad. They're not gonna be like text. Hold on, they're just gonna be varchar. My bad. I conflated the two types. So yeah, we're gonna have first name that's gonna be varchar or varchar 100. I don't know varchar or varchar or whatever. I'm gonna say varchar. Varchar 100. Um, or rather, I think it's varchar. Whatever. I don't know. And then it's gonna be not null, right? Similarly, last name. We have this is gonna be similar. Email. It's again gonna be. It could be varchar 255 or whatever. Varchar. Usually email are not that long, but let's just 150 or whatever. And then password, we're gonna use encryption for password, but that's not what we're discussing for this system design question. So password, and again not null, but everything else is same. And then created at, these are important ones. Created at and also updated at. They are both gonna be gonna these both are gonna be timestamps with default value set to current timestamp. Okay. Then what next? Then we're gonna have um here we're gonna have message, right? How does a message look like? So a message is gonna have um an ID, which is gonna be PK, AI, and an integer. User ID, super important. Um, User ID is gonna be a foreign key, and obviously not null, and obviously an integer. Um, and then we're gonna talk about the actual content, right? So content of the message, which is gonna be a rather a text because we decided that it's gonna be 1,000 characters and not null. And that's pretty much how the message model is gonna look like. And then no, obviously created at We can also have update that, but that is redundant because we are not going to implement the functionality where the user can edit the message, but we could have that, right? So again, it's going to be timestamp by default set to current underscore timestamp. Okay, cool. So we got message here, and then let me move it up here a little bit. So there, okay, hold on. Okay, and then we have chat, right? So chat is gonna have an ID, which is gonna be primary key AI and an integer. And then another super important thing we're gonna have here is a JSON object. So we could name it object or whatever you wanna call it. This is gonna be of type JSON and not no. And this is gonna be of the format. Format is gonna be so user one last active timestamp. User two last active timestamp, right? So these are how our, and by the way, these are the IDs. Um, these are the IDs of the two users. Um, yeah. So they don't necessarily have to be formatted as foreign keys, since it's gonna be like a JSON, but like that's how the two tables are gonna communicate with each other. So okay, so we got this here, right? Okay, so what next? So now let's talk about the implementation and what APIs are gonna be there, right? So I'm gonna clear the screen again. Okay, so we have like a user on their dashboard. They're gonna see like a number of chats, right? When they click on any chat, now they should be able to retrieve the messages. And every time, now, how do we get the messages, right? Obviously, when the user is like first logging in, they first click on the chat, it's gonna get all the messages associated with the two people um, in that JSON object. So it's first gonna get the chat, right? It's gonna be like, okay, select the chat with the ID this, got the chat, got the get the two IDs of the two people involved in that chat, um, and then get all the messages, sort them according to like their timestamps and stuff. Now, what if two people are logged in? Let's say me and my friend are logged in, right? Um, Me and my friend are logged in, and we need, now I send him a message, and how is that message gonna be pulled? Like two different strategies we could use here. Um, A, the push model, and B, the pull model. The push model dictates that every time a user requests, we pull the messages from the database or the cache, whatever storage. Now, what happens? What's the problem with that approach is that it's not seamless. Okay, so every time, if let's say I send message to my friend, unless he pushes the button, he's not gonna receive that message. That's not really what we want to accomplish here, right? So and also, if there's no message to return, like my friend would know whether there's a new message or not. So if they were to click on the button and there's no new message, then it's just gonna be like an empty request, right? So that's not very strategic approach, and also like increases the latency of the application because you're unnecessarily communicating when you don't need to. um, what is the other approach? The other approach is the pull model, which is the sockets. So we use sockets, um, and the way sockets work is this, right? So you have the client side of the sockets, you have the server side of the sockets. Um, the way a socket emits the messages and like receive the messages when on the server side, the socket WebSocket receives a message from the client. It also receives the client ID, right? So and that's what I want to talk about next, but let me first finish this. So I send a message, right? I send a message to my friend. That message is sent as a socket message to the server, right? And now that message is like the whole process happens there. Um, like we have a mechanism, we're gonna have a mechanism to store the message into the database and everything, and like update the cache and whatever. But we also emit back the message to the other person involved in that chat. So how that's gonna, okay, let's talk about that first a little bit. So we can store like a in the server itself, we can store like a local memory where we're gonna store like a mapping from the user to their client ID, whoever is logged in. If they're not logged in, then you return a failure. Just say that the person is not logged in. Um, so, but the message is still written to the database. Just you return that the other person is not logged in, right? Otherwise, the sending of the message is successful. Okay, so what we're gonna do here, we're gonna use, since we want to make the application highly available, the chat server. It's not gonna be just one chat server. There's gonna be like 3 or 4, and we can like scale up and down depending on the requirements. But we're gonna have like these 3 chat servers, right? We're gonna have load balancer, and based on what the client ID is, the load balancer can appropriately redirect the request. That's how it's gonna work, right? So, okay. So what's gonna happen is I send a message, the load balancer. Okay, let me actually draw it out. It's gonna be easier to understand that way. Um, so this is the, hold on. So this is me, this is my friend, this is the load balancer. These are like many chat servers, and then here's we're gonna have the database, but let's just stick here, right? Let's just stick with this. This is this drawing for now, this workflow. um so right, load balancer, this is gonna store a mapping of clients and their hashes. Okay, so yeah, so this is gonna be user 1, this is gonna be user 2, right? So, and these are the chat servers. So chat server 1, chat server 2, and then chat server 3 here. Okay, so I send the message, the load balancer is gonna be like, okay, Ishan is sending a message, and the browser he is sending the message from, that's the ID of that browser. Who is he sending the message to? So we're gonna have that API request here there, right? So I'm gonna talk about the APIs in a little bit, what APIs the chat server will be exposing. So send the message through the API, right? The request body is gonna have the ID of the recipient, which is user 2 in this case. It's gonna get the mapping. The load balancer is gonna get the retrieve the ID of the user based on the user ID. We're gonna store the mapping here. So like based on the client, um, sorry, yeah. So essentially based on the client user, whatever you want to call it. So the mapping is gonna be like we have client, which is more like browser, but like it's also like since a user has logged in using that browser, so it's more like from user to their uh client the browser's hash, right? So whatever, we get the hash. Okay, let's just call it, we get the hash. And I was rambling there for a little bit, never mind. We get the hash, and based on the hash, the load balancer is going to redirect the request to one of these servers. Okay, so wherever the messages are stored. Um, okay, so because we're gonna have like a lot of users, so not every single user is gonna be on the same chat server, right? So otherwise it's gonna overwhelm. So that's the mechanism we're gonna use for load balancer to redirect the requests. To make the load balancer itself more reliant, we could have like a backup load balancer here, like a second load balancer here. If the first one fails, the duty falls on the second one. But I'm gonna leave that for now. Okay, so that happens if the user is sending a message. It's gonna send the request to the appropriate chat server. The algorithm is gonna happen, the message is gonna be written, and then the load balancer is gonna try to locate the ID of the other user, right? If that ID exists, the hash, I mean, if the hash of the other user exists, all well and good, the message is gonna be emitted using the socket to this user. So we're gonna have the socket.io WebSocket on the server side here, and on the client sides, on the front end. So if the recipient's hash does not exist in the local storage, like in the mapping, we're just gonna return a failure that okay, the user is offline, right? We're gonna do that. And what's gonna happen is that on the front end side, whenever that message is received, that message is gonna be appended to the list of the messages being displayed on the screen. So that's how it's gonna work. Okay, so now let's talk about the APIs. I'm gonna clear the screen again. Clear my drawings. So I have to change the color again. Hold on. Okay. So the API is gonna be /get/chat ID. This API is going to fetch the messages based on these are the public APIs, by the way. Not talking about the private ones. We're gonna have like a lot more private. I'm just talking about the public ones here. So this API is gonna hold on. It's gonna fetch the messages based on the chat ID. So like I described in the data schema, you get that JSON object from the chat ID. There's gonna be two users in there, right? You get all the messages where user ID is either that user or the other user, like either user one or user two, and then you sort them based on their timestamp when they were created. So this and this is, by the way, we could just call it something like /chat/chat ID, and this is gonna be a get. And then a post request is gonna be to write, right? So it's just gonna be chat/send. Let's just say this API is gonna fetch the messages based on the request. Sorry, it's gonna write the message. based on the request, right? So body, request body. Obviously, these API routes, these APIs also are gonna be protected by some sort of middleware. So you're gonna have to pass like an authentication header from the front end. There's like multiple ways to implement that authentication. I like JWT method. So when the user is signing in, we return a token that's stored on the local storage. For every subsequent request, you're like sending that token, passing that token along in the authorization header that's being verified by the middleware on the backend, and accordingly the 401 status is returned or whatever. So okay, but that's not what I'm going to talk about for in this video. Okay, so how's the request body gonna look like, right? Um, so we're gonna have obviously the sender ID, the recipient ID. We're gonna have all sorts of like sanity checks in place so that if the ID does not exist, or if the ID is malformed or whatever, we're gonna return an error. We're gonna return like a 400 error, or 404, depending on whether the object is not properly structured or formed. Okay, the sender ID, recipient ID, and the message itself, right? We have this. Now, for this particular post request, you send the message, load balancer sends the based on the it first retrieves this hash of the sender ID, which it's storing in the local storage, right? It retrieves that. um Also, no, hold on a second. Actually, you know what? So when we're sending this post, we're also gonna send a message using sockets to the backend, like the socket on the load balancer, which is gonna get the ID of the sender and accordingly appropriately like redirect the request. Um and then it's gonna write the message to the database, and then it's gonna return a success depending on whether the data has been written or not, or maybe a failure. If it's a failure, we simply return. If it's like success, then we get the hash of the recipient, and the server, or in this case the load balancer, is gonna emit a message to this particular recipient that, here, listen, um this is the message which was sent. Hold on. Yeah, this is the message that was sent. And so yeah, and then we're just gonna append that message to the array or an array list or whatever is there on the front end, and that's gonna be rendered on the front end web page. That's how it's gonna work, right? Okay, so now with the API straightened out, let's talk about um the cache. Let's talk about the cache here, right? So we wanna have lowest latency possible, right? So we can have a least recently used cache, and the mapping in the cache could be um, user ID, or rather, um, yeah, user ID to the message object, where message is gonna be like, you know, user message time, like the created at timestamp, right? So we could, if the users are not very active, their messages are going to be wiped off from the cache, and it's going to be like fetched from the database. If they're more active, then their messages are going to be kept in the cache. And the policy we're going to be using is the policy where the message, in a single transaction, both things happen. The message is written to the cache, the message is written to the database. Because here's why. if I'm sending a message, odds are good that I might refresh my window accidentally or something, right? So it does not make sense when I'm sending a message to write it just to the database and not store in the cache, because there are decent odds I'm gonna need that. I'm gonna need that message again, right? So that message is also written to the cache in a single transaction. And we could now, the reason we also write to the database is because to make the application more fault tolerant. In case there's a power failure or something, the data is gonna be lost because it's just gonna be in like that, ephemeral stage. It's gonna be in the cache. It's gonna be in the browser, not the browser, but like the server memory. So we wanna write the database as well. Once data persists, once the transaction is successful, we return the success message. Okay. Um, Now, speaking of data sharding, so obviously we're gonna have like incredible amount of users. We talked about this during the estimation, 500 million users. So we're gonna use concept of data sharding. Um, if let's talk about the messages first, how we're gonna like short the messages, right? So we talked about in the estimation that we're gonna have um how many messages we're gonna have 500 million times 2 billion, 20 billion, right? We're gonna have 20 billion messages, right? And we're gonna have 500 million active users. We want to keep all the messages of a single user on and we said that every user is going to have like 40 messages, right? So we want to keep all the messages of a user a day, right? So we want to keep all the messages of a user on one database. So that means we're going to shard using a user's hash. So let's just say I'm gonna have to look it up, I forgot. So yeah, so let's just say that um if let's just say, where's the whiteboard, okay. Yeah, let's just say that one shard is of the size so hold on, I'm gonna like use the text box here. Let's just say one shard has size 4 terabyte, right? And then pretty sure based on our estimations we had like 36, right? They used 100 bytes for each message. I used 1,000 bytes. So yeah. So each database has each database shard. I'm sorry. We're gonna have a total of 36 by messages, right? So we're gonna have, that means we're gonna have approximately 9,000 shard. For the sake of simplicity, we're just gonna say 10K shards. And then to find uh, the correct database, we're gonna use users hash modulo 10K, right? So yeah, that's the database sharding. Um, and yeah, that's pretty much it. That's how the application is gonna work. That's the underlying implementation of everything. That's the architecture. Um, Extended requirements, we could also have like images being stored in a separate CDN, and we could implement that. We could also implement group chats. In that case, we're gonna have a different kind of in the same chat table, the JSON object could have like more than just two users, and then we could get the messages and like obviously um, update the clients using their client IDs using WebSockets appropriately. So yeah, that's pretty much it. I'm gonna stop sharing. This was my first time recording and practicing how to do a system design question. I'm pretty sure I must have made like a lot of mistakes here. Um, and I had to look up a lot of things for my reference. I'm using this great website, educate.io. Um, and I'm gonna post this on YouTube for a while. I'm gonna take it down because I want to share it with my friends and see what they say. Um, so yeah, that's pretty much it.